How are you?
I'm doing very well, Brian. How are you?
I'm doing well. We were very concerned, or rather, the internet was concerned that we were scheduling last week's podcast over the World Series. How cruel! And that they were going to have to miss the World Series game.
Yeah, missed
Or
that
actually,
whole game.
I guess it was more that they're going to miss Oxide and Friends to watch the World Series game. As it turns
Yeah.
out, they would have only missed the first third of that game.
Yeah.
Because that game, I tuned into that game in the 10th inning and watched for 3.5 hours.
We ended at 6:30. That game went until almost midnight. There's still plenty of game left.
No, it was amazing. And did you watch the game? I assume
I listened to it on the radio because I don't know why, because I'm a psychopath, I guess.
Did you watch the entire? It's my understanding that people really love it when we go deep into baseball. So did you watch the rest of the World Series?
My wife's birthday was conflicted with the World Series, so I prioritized that. But then we watched Game 7 as a family, and it was fun. And except for Canada, so I'm sorry, Canada.
Why did they not send the runner, Adam? This is you're a baseball scholar. Can you explain to me why? I mean,
Falefa on that play
yes.
at the plate.
No. When you got runners at first and third with one away, and you've got Kirk up. Why would you not send the runner from first to second to get out of the double play? So I was just like, get out of the double play. What are you doing?
Because I think there's too much risk of him being thrown out. Because I don't think he's a great runner.
Then get someone in who can if you serious. If you cannot take that bag in that situation, you just should never be on a base path. You know what I mean?
Yeah, I don't know. I mean, it's kind of high.
One out and a runner on third. You really think they're going to gun you down at second? Score the plate the runner.
Yes, I do think that they're. I mean, having just
who's on the track team in the dugout. Get him out there. I don't know.
I think they've been in the game. I think they I mean, at that point, you'd kind of gone through the people who knew how to play baseball.
With the benefit of hindsight, though, I mean, it was a GIDP. It was a ground in the double play.
Yeah, God, what a brutal way to lose. I mean,
it's hard to do with a runner on second and a base bag open. Dave, you're
look, if you're auditioning for your next role as a Major League Baseball coach, I mean, I know that you had been a Little League baseball coach for many years.
I'm thinking more like podcast.
I know you would have sent that runner in a heartbeat on your on your Grasshoppers team or whatever.
Well, listen, the catcher would just going to sail it out into the outfield. Like, why would you not?
No, I guess that makes sense.
No, that's the class play where you have the guy in first walks to second because they're trying to bait the throw, so you can send the runner home.
Good. I know it worked in your Little League. Why would it not work against the Dodgers? I guess that makes sense.
I got to say, send the runner. Will Smith's got a good arm. Send the runner. Get someone on the track team again. That's all I got to say. But it was an amazing World Series. Also with many amazing pitching narratives. I'm obviously a bias. Will Klein, the pitcher for the Dodgers in that 18-inning game. I mean, you had to root for the Dodgers in that game based on Will Klein's performance. It was amazing. So there you go. I think I've said my piece.
There we go. When would you have said the last time we talked about async on Oxide and Friends was? Like, maybe you've already looked it up.
When I can't recall, and I haven't, I meant to look it up and probably should have looked it up, but did we ever discuss 397 and 400 here, or did we merely talk about the need to talk about it here as Rain unmutes herself?
I think we only talked about the need to talk about it here, and then I was like, "Hey, this is not going to happen here. Let me go do it at RustConf," and then I went.
Rain! Oh, wow! oh man! I'm so sorry. You're just like, well, the podcast doesn't want this, so no, that's not it at all. Okay, yeah, I feel bad. Which obviously, Rain, I'm sorry. Let me just get that out there.
Oh no, you're good. You're good. It's all in jest. Yeah.
But we obviously should have talked about the async cancellation issue, which Rain, I mean, really for the better of humanity, if that's what inspired you to give your RustConf talk, because a really extraordinary RustConf talk, and a great blog entry that accompanies it. on that issue. And was that, Adam, was that the last time? Or I guess the last time being that time we didn't discuss that. What was the last time? So it was the last time
we talked about it in like June.
in June with the other issue, when we were talking about state maps.
Yes, exactly right. Yeah.
And so yeah, we are back again with another and Dave, I don't know how we want to pick this up, or John. So we are once again, we find ourselves just trying to ship a product really over here. We're really not trying to find like new pathologies in the language, I don't think, or I think we're just trying to ship a product and something that's robust and works. But we have found ourselves here again where we have found something that is a pretty deep pathology. But John, do you want to kick us off with kind of how we got here? Because I think the story that you told, I thought, was really really compelling and interesting in terms of what the symptoms were. How did this start? How did this odyssey start?
Sure. I should probably hand it over to Dave pretty quickly. So what happened was we have been testing live update, right? Which I think we've talked about some on the podcast. So this is like the entire Oxide rack, which is a distributed system, updating itself while the control plane remains online. And we had done we've been trying to get a bunch of repetitions of that in play on what we call our dog food rack, like the rack we host at the office. So Angela, a coworker of ours, had kicked off another update. These take several hours to run because the whole thing stays up, so it just updates one thing at a time in the background. And she had kicked one off over the weekend. I think this was 3 weeks ago, maybe? I don't know, 2 weeks ago. And she filed an issue saying after a couple hours after the update, one of the Nexus instances, Nexus is our main API server that's reachable from the outside, one of the three was unresponsive. And I think I should hand it over to Dave at this point, because Dave, I think you actually got on Sunday to just kind of like poke around a little bit and see like how bad things looked. Is that right?
Yeah, that's right. I'm not sure why I did, but I just happened to be checking chat and I was like, maybe this will be something easy. And so I just basically spent a couple minutes looking for the easy things, and that was disappointing. Basically, yeah, so Angela had reported that we had that this Nexus instance was hung when you tried to make requests to it. That was easy to reproduce. So then the obvious thing is I tried to make different types of requests to it, especially ones that I thought it could fail very quickly. So like something that's not even a valid API, that's not a URL for which we have a handler. And it's returning successful or error responses for that very quickly. So that's pretty informative. So the process is not totally stuck, but it's stuck doing something. And then I managed to find an API endpoint that did something non-trivial that also succeeded, which was sort of the first hint that like, okay, something specific in this thing is hung. And then the question is, what is it? I don't know how much I actually did that day, but the next day or at some point we kind of dove in some more. Should we just like keep going with
Yeah,
how the debugging went down?
Yeah, I think it is helpful to kind of take this from the outside in terms of debugging this, because I do think one thing that's really important to understand is the kind of the nature of this pathology, which is pretty hard to debug actually. Actually, you've got, I mean, not to give away any spoilers, but let's just say Ghidra becomes involved at some point. So what's next? So you got a Nexus instance that appears to be hung, and is hanging on certain kinds of operations.
Right. So the natural next thing is I start digging into the logs, and I see the last log that we completed, which was I think it was an authorization. We successfully authorized some trivial thing within the process. It was like we were trying to see if we could query the database, and we said, okay, yes, this user can query the database. And then we got stuck. So that suggests that we were about to go do something with the database. So I did the sort of obvious thing and looked for duck database transactions or connections. Like I looked into the database CockroachDB and was like, what? I did a query that was like, what are the current running queries from this particular host? And it was nothing. It hadn't made any queries in several hours at that point. And it wasn't currently stuck in a transaction. So that kind of ruled out the obvious things. Like we somehow got stuck on some database lock and everything behind that. And that's when we sort of like, from my perspective, we had to bust out the sort of like big guns, the sort of much more time consuming and error prone debugging, which is the sort of, this is where I busted out the PID provider tracing of the Tokyo task activity and the drop shot activity. And this was kind of based on back in June when we had debugged a different problem, it was not a hang, but it was sort of similar, where something would hang for like 10 minutes or something like that, right? That was the problem we were debugging back in June. That one turned out to be a problem where the Tokyo scheduler was not picking up a runnable task when it should have, but it did eventually pick it up and did eventually complete it. Things were just getting stuck in the meantime. And so the sort of obvious thing, if you're like, well, I don't know what this thing is getting stuck on, is, well, I'm going to start tracing everything I can in the process between a point where I know it ran and a point where it stopped running. And I was able to use the probes that Eliza had added after that bug from back in June to have a much simpler way of tracking activity by Tokyo task. And from there, we were able to see what was going on, which was the thing was basically going to sleep. What were we able to tell at that point? I think we were able to tell that it was the task was going to sleep, trying to claim a database connection from Corb, sending a message on an MPSC channel in Corb. So basically, Corb. Go ahead.
Corb, QORB, which is doing connection pooling. That Sean wrote, right? Inspired by the cue ball work at Joyan. And then you're using, just to fill in a couple of the things you went by, the instrumentation that you're using is the instrumentation that we used after this episode. I mean, episode both, I guess, metaphorically and literally, because we of course did a podcast episode on it. This is the When Async Attacks episode. If Adam hasn't already rung the chime by now, he will ring it here. One hopes. That is to say, future Adam, not present Adam, which has no chime towers.
Yeah,
exactly. No, it's future Adam. Which by the time people are listening to this is actually past Adam, but a little bit.
Very confusing.
But so, and Dave, you are using, and we talk about using the PID provider in Tokyo, and then the probes that Eliza added. You're just trying to you're kind of like, where the hell is this thing? Right?
Exactly right.
It's kind of like,
what are the instructions that are executing?
Right.
Tell me anything about what's going on, basically.
We should say,
yeah.
Well, there are also probes in Corb itself, many of which were added after the debugging adventure in June.
Yeah.
And that they were good, but just more confusing, right? Like the things that the information we were getting from Corb made no sense to us, right? So Corb is sort of like your standard actor pattern, right? So it has it's when you create a Corb pool, it has spawned a Tokyo task that is just receiving off of a Tokyo MPSC channel. And it's running a big loop, right? Like polling for messages on the channel and some other internal bookkeeping stuff. And the probes that Sean had added, we were seeing Corb's internal bookkeeping fire every 60 seconds, just like it's supposed to. So that normally, if you can't talk to an actor, the assumption is that the actor has gone out to lunch, right? That's the normal pathology we've seen in the past. It's like all these things are queued up trying to talk to this actor because the actor isn't pulling messages out. But Corb was running. We saw every 60 seconds, it does its bookkeeping. It takes 100 milliseconds and then it goes back to sleep, which I think multiple times as we were looking at the code, we were like, I don't understand where we could possibly be stuck based on all of the senders seem to get to the point where they're trying to claim, which means they're sending a message to Corb, and Corb on the other end is just happily running along in the background, never returning claims, but still doing its internal bookkeeping every 60 seconds. That's about as far as we were at this point, I think.
Which doesn't make a lot of sense, but is also really important data points, and this is what I love when you kind of gather just facts about the system that seemingly don't make sense. That kind of any future hypothesis has to accommodate these facts. It's actually helpful to have them, even though I'm not sure. Did it feel helpful at the time, or did it just feel? John, I remember at one point you mentioned one of the hypotheses was we are actually observing the wrong Corb. The Corb that we are actually observing is one that is much more functional. We are somehow maybe something's going on and we are observing the wrong thing. I mean, you're beginning to ask yourself because things are not making sense.
100%. What you said about facts that reject hypotheses. Like nearly every hypothesis we came up with was rejected based on the facts we had, right? Like it just, we were like, we have to at least be getting here, but we have evidence that we're not. So like any theory that involves we're getting stuck at this point along the way, we get to throw out because we're not, like, we can see from the evidence that we're not even making it that far. I think
As
we
an example,
had,
we were able to tell from what we had that we were not stuck on CPU. We also looked at CPU utilization. Like, it wasn't like the cores were pegged. We could also
Right.
see the thread that we expected to be running these things was going to sleep and not picking up other tasks. So it's not like we didn't have a Tokyo task. It's not like we didn't have a Tokyo task to run this thing. Right? We could tell that we were idle and Tokyo didn't have anything to run. That like ruled out a bunch of theories. And as John said, we were staring at the code and it's like there's not that much explanation for what's going on at this point.
yeah, we should say, so one thing to clarify is that when we say that everyone trying to claim a connection was going through an MPSC send call, right? So the handle to core, which gets cloned all over the place, is basically just a wrapper around an MPSC sender. The channel is of size 1, which is relevant later in the story, but like is not immediately obvious at this point why. So all of the senders, the only thing that goes into that channel is we use the normal send function, which is just like send message.await, and it blocks forever until it's able to send on that channel. So the only two theories we had at this point, spoiler, neither of these was right. The only two theories we have are that, yeah, one is that we're observing a different core pool. Like, have we somehow spawned two database connection pools and we're seeing like one working, but the other one is
which, to be fair, we believed from code inspection was impossible.
That's
also.
right. That's right. The other theory, which I think all along I claimed was like statistically impossible, was that somehow the Tokyo MPSC channel itself had gotten broken in some way, which, I mean, we are far from the only user of that, and we use it hundreds of thousands of times a day in 1,000 different contexts, right? So the idea that somehow we've tripped over some weird edge case inside the channel itself seems impossible to me, but I have no other theories at this point about what could induce this behavior.
I mean, Eliza's saying in chat that this is about when she got her subpoena. I mean, it must feel like, I mean, did it feel a little bit like Murder on the Orient Express, where you have like, as the four, because the four of you, Dave, John, Eliza, and Sean are all debugging this together. And all of your software is kind of intermixed in here. And obviously, like, you know, I mean, obviously, blameless postmortem, of course. But meanwhile, each of you individually must be thinking like, shit, is this like, damn it, I really wrote this code carefully. Is this, I mean, or were you, did it feel like force majeure? Did it feel like it was transcending any one of you? Not to personalize it.
I feel like it was still very unclear at this point because it seemed so impossible, you know, and I wanted it to be in some code that we controlled more easily, like in Omicron or something. But we had a couple of conversations where we were like, is there any way this could not be a bug? Like, how could this not be a bug in the Tokyo channel? Like, it doesn't, like, I don't think any of us was convinced it was, but we could not come up with a way in which it wasn't based on just looking at there's only 2 or 3 code paths that touch this channel. And what we were able to determine conclusively from the tracing was that the senders were going to sleep on the sending side, and the receiver side was frequently polling that thing and finding no messages. It's like, how is that possible? And if you know the answer, it's like, well, actually, I guess it's kind of obvious, but it was very not obvious at the time.
Very not obvious, yeah.
There's a bit of an oversimplification of like our mental model that was here, which is you have a MPSC channel and you have a receiver that is awake, alive, pulling values off of that channel and is not getting stuck, then senders should be able to send, right? Like, things will get through the sending side as long as they're pushing things through. So there are details that I'm leaving out here intentionally, but like with that mental model, we see the receiver is waking up to do other work. Like that task is waking up and the channel appears empty. So that really felt like a major like violation of expectation, that the channel seems empty, yet no one can put anything to it.
Right.
Yeah, so
and it's John, go ahead.
Well, the thing we decided to do here was like, can we collect more information about the state of the channel? So I think it's about at this point that Dave collected a core from the process at the point it was calling receive. So like from the perspective of the thread that happened to be running the corb actor task, the instruction at which, like the first instruction inside receive, collect a core there, we can load it in the debugger. And then
John, can we just pause just for a heartbeat, because this is a technique that we have used a decent amount on our most vexing problems, but I think it's a somewhat unusual technique. Dave, can you just describe a little bit about how you were collecting a core dump from a process that was not dead?
Yeah, so this was dtrace PID provider for the win here. This was basically looking at I think I looked at the trace first. So I guess backing up a little bit, I didn't really explain what I had traced earlier. When I created that trace earlier, I was using some dtrace probes that we had created with USDT from Dropshot around the HTTP request handler, from Corb around its claiming database connections and stuff, and also the dtrace PID provider, which is capable of instrumenting most instructions in userland processes and also function boundaries, so entry and return. Is that a fair summary? And so I was trying to trace everything in Tokyo and everything in Nexus, which is our program, but not everything in the whole process, because there were way too many symbols in the process, and that was too much to trace. From that trace, we were able to see the Tokyo functions that were getting called, which included the receive, and then I was able to use that to trace. So I created a new de-enabling that would trace entry to that function, and I stopped the process there using the stop action, which is the destructive action in dtrace, and I ran gcore to save a core file at that point, and then prun to run the process again.
So this is where we're going to get the process into a state that is interesting to us by using dynamic instrumentation, and then we're going to use gcore to grab a core dump of it, and now we've got everything that is static in this system. Now we can actually go study this thing offline, and study, maybe putting that either literally in this sense, John, because at this point you've got a core, but the core is a limited utility, in part because of some of the way Rust operates.
Yeah, that's right. I don't know if anybody's had the pleasure of trying to read assembled Rust, but it's challenging. So at this point, I spent the better part of a day with Ghidra. So I loaded Nexus into Ghidra, which Ghidra was a champ. It took like 45 minutes to just do its initial analysis of the binary. But I'm sort of like source assisted reverse engineering, I guess maybe the right phrase for it. Like it feels like reverse engineering because there's been so much inlining going on, even though I have all the source to our program and the Rust standard library and Tokyo, etc. So I think there's some walkthrough in the issue that is linked from the RFD. So I don't know if anybody's ever done reverse engineering like a malware or whatever, but it's like a very unglamorous task. You just sort of spend hours staring at assembly, trying things. Eventually, I'm able to convince myself that I can track through like the particular bits of the channel are in these registers at these point in times, and the things that we care about to look at are at these offsets from these registers. And I guess we can, at this point, we're like really digging into the internals of the channel just to understand what that is. So an MPSC channel, this is going to be a little oversimplified, but not a ton, is a semaphore and a linked list of blocks that hold the actual messages. So from the receiving side, the thing we could look at was what's the current state of the semaphore, which it said there were no permits available, which is consistent with all the senders blocking. But maybe is a little surprising if we expected like someone to be able to send into it. And there were also no messages in it. So like we can look at the current head of the linked list. So that block will hold 32 messages. And we could see that we were like 26 or 27 messages into that block. And we saw all the old messages and we see space for the new messages. And like at this point, we're like, well, this confirms everything we've already seen, which is that from the receiver's point of view, this channel is empty. There are no messages here. It is calling receive. The arguments all look right. Nothing looks corrupted. It's just an empty channel.
Which on the one hand, is okay. This is like vexing because this is still like, there's still obviously a huge mystery here, but we've got a lot of things that are at least lining up, right? This is not rampant data corruption. We've got maybe some other fears that one might have. It's like, this program is in a state that we do not understand, but we have some self-consistency here. I mean, I assume that was of some solace. maybe it's easier to say that after the fact. Exactly.
Yeah,
Some
I think
solace.
that's right.
Yeah, all right.
I mean, there was definitely a part of me that was hoping I would look at the like current permit count in the semaphore and see, just garbage, right? Like that in some ways that would be more of a relief, right?
Oh, well, I'm glad that you would have been very relieved by that. Meanwhile, the rest of us
Well,
with a reliable computer would have been terrified by it. But yes.
Play back the recording. I don't think I said very relieved. I think I would have said somewhat
exactly.
relieved.
Fair.
Yeah.
Exactly. Fair.
It would at least explain the symptoms that we had no theories for, right? Like we seem to have an empty channel with 180,000 tasks trying to send to it. Like this doesn't make any sense, right?
Yeah.
I think this
Go
ahead,
Oasa.
This is when I think John started asking me some questions about the semaphore that started to make me feel really uncomfortable.
Right, exactly. Like, I feel I need my lawyer present for these questions. Why are you asking me such a pointed question? Right.
And we did some stuff. One, we did like a lot of just walking through the semaphore code and looking for things that looked like potential like issues that might have caused this weird behavior. And it's hard to do that because the last time this code in Tokyo changed substantially, I checked the blame, was when I rewrote the semaphore 5 years ago. And so it's been like that for 5 years. And if there was this bug in it that caused it to, fail to distribute permits in the way that it's supposed to, that bug, somebody should have seen that before this happened to us, right? So it feels kind of implausible, but
it is implausible. But I love, Eliza, I just love the trepidation in your voice where you are clearly telling yourself this in the mirror, because you also must know that, like, well, it's definitely possible that someone would see this pathology and not be able to dig enough to. I mean, it feels like it's extremely unlikely, but not impossible.
This is about where I think some combination of Dave and John and I started coming up with like scenarios in which we thought something might misbehave that I think involved like possible races around acquiring and dropping permits. And I wrote some like Loom tests. Loom is a concurrency model checker that Carl Erica wrote while he was rewriting the Tokyo scheduler at about the same time. And it essentially does like a simulation of possible interleavings permitted by the C++ memory model, which is the memory model that Rust atomics implement. And it can be very useful for finding this kind of like weird deadlock where maybe some particular ordering of events results in something happening. And so I started trying to write some tests that I hoped would trigger this kind of hang based on some of the scenarios we were dreaming up. But we could not get anything to break, which was pretty unfortunate.
So what's the next breakthrough at this point? So, I mean, first of all, I love that about like, okay, let's go back to some of the tooling that we've got in terms of Loom to go see if we can go induce this in a way that we can detect it.
So, I mean, the next thing we did, this was another fool's errand in hindsight, but the next thing we did was collect a core from one of the senders. Right, so this didn't go quite as smoothly. I don't know, Dave, if you want to talk about that. We ended up accidentally killing the process in the steps to collect this core.
Yeah, so I was going to mention there's this context that I don't think we've actually said, or maybe it was implied, that we have never seen this problem before, and we had no idea what triggered it at all.
Right.
And it's a complicated system. It's a complicated control plane. It does a zillion different things. So we had no idea how to reproduce it. All we had was this one precious process. And that's why we were doing these sort of the sort of production-focused debugging in terms of using dtrace and tracing these individual things and trying to get core files and disassembling and try to pick the state out, because we had no other way to get more information except from the live system that had hit this. And then, I don't know how much it's worth going into the digression, but I tried to do the same thing on the send side and I forget exactly what problem I ran into. I called in Adam for some help, and then I did something I shouldn't have done. And I think I tried to use MDB with no stop so that it wouldn't stop the process, and set a breakpoint, and then exited. And
yeah, you want to guess how that one went, Brian?
Not well. Yeah.
Well, the good news is we got a core file.
And I bet you can guess what instruction it was on.
Yeah.
We got a core file in precisely the context we wanted a core file.
There you go.
Right. That's the good news.
That's
the bad news is there will be no future core files because this core file is actually the last core file from this process. This process has now died.
That's right.
Okay. So now with the killing of that, have we now lost the problem?
That we did, yeah. But John, do you want to talk about what you found from that one?
Sure. I mean, the main thing because remember earlier we had two theories. One is like the internal state of the channel is corrupted somehow. The receiving half everything seems fine. The other theory we had was maybe we've somehow spawned two pools. So we're like, if we collect from the sending side, we can at least see if they're talking on the same channel. And we were able to confirm that. So from the core collected on the sending side during the death of the process, we confirmed that it was the same channel and that the channel state looked the same from the sending side. Like there are no permits available, which is like that explains why all the senders are blocked. So I have a comment from the issue that basically like after we did the analysis of both of these cores, like the internal state, according to both cores, it's consistent with all of the evidence we had seen from the DChase probes, which is that the semaphore has no permits available, therefore all the senders are blocked. And also, the channel has no messages in it, which explains why Corb is continuing to process but not handing out any claims. And I wrote down in the issue what our theories were at this point. One was a sender had grabbed a permit and leaked it without inserting a message at all. Second was a sender had grabbed a permit and was still holding on to the permit but wasn't inserting a message for some reason. A third one was the receiver, which is the Corb actor, had gotten a message out but had failed to put the permit back into the channel somehow. Or the fourth one was this gets into like the details of how the channel is implemented, which actually is relevant in the way we ended up tracing the problem here. So this channel has size 1, which means it nominally has a semaphore with one permit in it in its sort of initial state. Once senders have lined up to send into the channel, when the receiver pulls a message out and goes to put a permit back into the channel, it doesn't start by putting the permit back into the semaphore directly. Instead, it goes to the first sender waiting in line. Right? So this channel ensures fairness. Like if you have 10 people call send at once on a channel of size 1, the first one puts their message in, the second one blocks. Once the receiver pulls the message out, it's going to go give the permit directly to the sender that was second in line instead of putting it back in the semaphore and letting like everybody race for it or something like that. So the last idea on our theory was, did we actually give the permit back to someone but then fail to wake them up? Like is this like a missed wake up of some kind? So those were the 4 theories we had at this point.
Is that the same as the second one? The second one was the sender grabbed a permit and is still holding it but not inserting a message. That's right. Is that the same as the fourth one, or is there a different thing you were thinking there?
I think we were wondering, I think it's the same pathology but different reason, right? Is this someone got it but is failing to insert, or we gave it to someone but failed to wake them up? Right. In either case, like the sender is holding the permit but is not inserting a message. It's just a question of why.
And I think that, John, I put this in the chat, but you can find the current theory that you just described, you can find by searching for one more wild theory, which was what you added as you're trying to like go through what are the different things that can explain this. And that last one you described is kind of the wild theory bucket. And so now what? So so the problem we've got some ideas of what this could be. And now what's the next step to go investigate this? Because has the system righted itself when we, or is the system just like killed itself completely at this point? in terms of the system in dog food?
So at the time, only one of 3 Nexus processes had gotten into this state, and that one
Got it.
was totally corked. But the
That-
other
that-
2 were working fine. The rest of the system was basically fine. And so that process died, but it came back and I think was fine. I don't remember if
It
we
was
actually
fine.
checked
Okay,
that,
yeah,
but
got
I
it.
think it was fine.
So we are
Yeah,
now
I
in the position of like, okay, we've got to now figure out, do we take kind of a half measure in the system to debug this? We believe we're going to see this again. We hope we're going to see it again. And
Well, and also, I don't think we'd given up from the data we had. I think we were still trying
Okay.
to figure out what can we figure out from this core file that we did get. And I think it was when we were discussing, we had just gone through and figured out what the channel state was when we started talking about these 4 theories and theorizing about what could have happened, right? Am I remembering that right?
Yeah, I think
Otherwise,
I told things slightly out of order. The bit where I think the sort of the last thing we did, which I described earlier, was actually look at the content of the linked lists storing the messages. So each of the requests to Corb has a claim ID, which is just an integer. There's like a thread local integer, incrementing integer. So we could actually see from the message block that, like, I think there were 26 old, and we actually saw their claim IDs like incrementing by 1. And then we saw that there were like 5 empty slots waiting for new messages. That was sort of the last thing we did. It was like the last hope of, I think maybe even Eliza said, like, she didn't actually write the message block. Maybe there was a bug in the way the message block handle, so we're like digging through trying to figure out if there was any evidence at all that like the sender had actually put a message in there, but the accounting of the bit mask of which slot was available had gotten off in some way. And we basically ruled that out from the course that we'd collected.
This is where John did some very cool debugging, because we realized that these linked list blocks are actually reused and are potentially uninitialized, so they might look like they had data in it that was valid even if it's not actually from that pass around the ring buffer. And John was able to figure out that there was this counter that's being incremented, and so we could actually see like where the edge of the most recent lap around the ring buffer was. But of course, it all just was like normal and fine. And
right.
And then we're just sort of sitting on this call, scratching our heads, and that's where we've ended up.
So you did not. So that's what it was kind of like having. Have a lot of constraints on what the system. How the system was acting in a lot of ways. Did you not have to see it again to debug it?
No, we
No.
didn't see it again. I think it was about.
Damn.
What I remember at this point was Sean asking the first leading question that brought us to the answer. Does anyone
Yeah, I do want to make this. I need to talk with you to figure out. But I think we can make because we actually recorded this. You recorded this because you're recording the debugging session.
Yeah,
and it is actually remarkable. It is literally a passing of the baton from. It's like Sean, Eliza, John, Dave. And it is really, really, really remarkable. Sorry, Dave, you want to describe the kind of the thought process there?
I don't know. Does anyone else have the transcript up? I remember Sean asking some. Oh, go ahead, John.
Yeah, I was going to say, I think we didn't get the automated transcript, but for the purposes of the demo talk last week, I went back and manually transcribed just this like 30-second snippet. Do you want me to just read what I have?
Yeah,
because it was amazing.
We should each say our parts.
There, I think Sean, if you want to start, we'll walk through it.
And action.
All right, sure. So I was asking, we were sort of at our wits' end with the existing theories of something being wrong with Tokyo channels. So we sort of took a step back and asked, how could this situation happen in our existing code base? Would this be explained by a caller pulling send, waiting there, and then not pulling again, but also not dropping to relinquish the permit?
At this point, I say something that's not quite in the transcript. I don't see how that can happen and I think it's because we looked at the code in Tokyo send and saw that it waits for a permit and calls await to do that, and then immediately sends the message. So there's no opportunity for it to not send the message once it has the permit.
And then I was asking if there was any possible construct that we had set up, such as using a Tokyo select statement, where on one arm we're trying to use Corb to get a database connection, and in a different arm, we do something else, but for whatever reason, we don't leave the function, we don't drop the first pulled future in the select.
Well, in order for that to happen, the select would have to select on the thing that's doing the send, but use a mutably borrowed future. I may have said and mute. That sounds like the type of thing I would have said, so that it doesn't get dropped if it doesn't complete. And then the other arm of the select, the one that we actually go into, would basically just have to have a loop that never returns in it.
And I said, what if that other arm is itself trying to acquire a database connection? And then if you post the recording, you get to see me staring like an idiot at the screen for about 15 seconds solid.
It is about 15 seconds. It is about 15 seconds. And actually, I don't feel this transcript is complete because I think this is I think that Dave, you in here say, did John just blow up all of our brains? Something
said,
like
John
that.
Just drop a bomb.
John dropped a bomb. That's what you said, right? Exactly.
Yeah.
So there's 15 seconds of stunned silence, which unfortunately, due to Google Meet, we only have John, you like kind of staring into space.
Yeah,
it's worse than that. I'm blankly into space.
Yeah, but it's so much worse than that. I'm like staring up at the ceiling, so you're like looking right at my. It's awful, right? It's terrible. So at that point, like after the 15 seconds, I sort of tried to put together everything the four of us had just said, and said, okay, you would have to have a select where one arm is selecting on an ampersand mute future that is trying to acquire a database connection, and that. Like we got into the send at that point and then returned pending because the channel was full. And then we go into the other arm. For some reason, that other arm becomes ready. And then within the body of the other arm, we try to acquire a database connection again, which means we try to send on the same channel. And now we're behind we're behind our own other arm in line in this fair channel.
Yeah.
And at that point, Dave, like without missing a beat, says, you just described the code that I'm looking at.
Yeah, well, I mean, I didn't follow this in real time. I didn't understand what you guys were describing in terms of the failure mode, but I recognized the code pattern you were describing, and I was pulling it up. And then you got really concrete in terms of like the select arm does this, and it's a mute future, and I was like, I'm looking at that code right now. Tell me now how this can cause this problem. I still didn't understand it at this point.
Okay, so then at this point, do you go, because I've actually not watched the recording from I need to go watch the recording from that point on, but John, at what point do you all like say, hey, if this is the case, we might be able to reproduce this in a smaller, like outside of Omicron, which would obviously be great.
I would have to look at the recording, but I feel like it was almost immediate.
Yeah, I think you were particularly intent on, it was either you or Sean. Somebody left that meeting like feeling really worked up about the need to write a minimal reproducer for this. I think it was either you or Sean for sure.
Yeah, it was. I think
suggested exactly how it should be reproducible. Like it should be really easy and 100% reproducible, which it was, right?
Yeah, I think I said unless somebody else is dying, it would be cathartic for me after spending the last 16 working hours in Ghidra to write like a minimal reproducer for this. That would be very nice. So I left the meeting. I think I had a reproducer up while we were still in the meeting even. It only took like 5 minutes once we understood what was going on.
And then it reproduced the problem.
Yeah, immediately.
Dave, like this is what you and I have called the software engineering equivalent of the walk-off home run. Totally. To go back to baseball. Yes. And that is just like a ball game. I mean, that must have felt great, John.
Particularly referring to the reproduction. Like I've been staring.
I've been staring at this. We've seen this bug once. I've been staring at it. I know there's so much now I understand about this. Wait a minute. If it's this, is it this? If it's this, I should be able to reproduce it this way. Going to reproduce it this way and seeing the exact same symptoms. It's just like, I mean, that's a ball game. That's it. So, ball sails into the night sky. That's it. Rounding the base path. I mean, John, it must have felt great.
100%. Followed up very quickly by, oh God, how many other places have we done this?
Right. Well, listen, have the celebration at home plate a little bit before you get to yeah, right. Where and this is where you kind of get to the analog of like, oh shit, is this like the async problem of like, okay, so, and maybe now it's worth describing a little bit, Dave, what you put in the RFD about like, okay, why do we feel that this could be pervasive? Because we need there are a bunch of different things that have to line up to hit this.
Right. So should we sort of re-summarize like the crux of the problem here?
Yeah, that'd be great. I think it would be great to do that.
The problem is basically we had a Tokyo task that was running a couple of different futures using Tokyo Select. One of those futures was going off and doing a database operation. That would use this MPSC channel of size 1. Although the size is kind of a red herring. And then it would get blocked on anything. Like there may have been a transient point where that channel was full because the receiver hadn't picked up the message from something else that was trying to get a connection to the database. So the Tokyo Select is also selecting on a different branch, which I think was a timeout. And then in that branch, in the arm of that other branch, it would go do something else with the database. What it was actually doing was it was collecting a support bundle, and in that other arm, it was checking whether that support bundle request had been canceled so it could stop doing this thing. And so you basically had pulled on one future that wound up putting itself in the queue to send a message on this channel, and then pulled on a different future that resolved, which was the timeout, and then entered a branch that would go in, pull on a different future, which would also try to send a message on the channel. But now, that's the only thing that task is pulling on, is that second future, but it's actually blocked on itself because it's blocked on the first future that currently has the permit. So this can happen, I mean, there's a lot of ways this can happen in principle, but where it would happen most likely is in a situation where you've got a task that is pulling on multiple futures concurrently, or it has pulled on multiple futures, and is now only pulling on a subset of those futures. And that subset depends on the previous futures, the ones that it's not pulling, completing. Does that
And this is where
make any sense?
Yeah, and I think this is where the task versus future distinction is really, really important. Load bearing, obviously.
Yeah, that's a good point. So tasks I sort of think of as the Rust async analog to threads, which is like not quite right, but like you can go spawn tasks in their individual schedulable entities in like the Tokyo runtime. But futures are the unit of asynchronous work. So every task has sort of one top level future, I think we can say. But that future may itself concurrently pull a bunch of other futures. So you can have concurrency without parallelism, without multiple tasks in this way, using select, and there's other constructs that let you do that.
Yeah, the way I often speak of this is I like to say that if you understand the difference between concurrency and parallelism, a future is the unit of concurrency in async Rust, but a task in Tokyo is the unit of parallelism. And that's really important to understanding like this bug and also how to avoid it.
That's right. And like, why would you not just do everything in a task? It's like, well, they're a little heavier weight. It's heavier weight to create a task. And there are also reasonable spots where you'd want to actually have concurrency without parallelism. You don't want to actually have the cost of parallelism in terms of either memory or potentially in terms of CPU, but you actually still want to have concurrency.
Well, not only that, but cancellation can be a feature, right? Like in some circumstances, like you want futures because like you want the feature of cancellation as opposed to the curse of cancellation. Like if you're trying to time out a call or whatever, like it's a very convenient way to build that kind of state machine. So
yeah,
I think it's not as crisp as like the heavyweight or lightweight of it. It depends a lot about the intention of the code.
Yeah, interesting. And in this case, we deliberately, because Adam, this construct that is the particular spot we hit this is kind of exactly what you're talking about. We have a timeout. We actually want to time this thing out if it takes too long. Yeah, so it's actually quite reasonable for that not to be in its own task.
That's right.
So I think on that debugging call, like after we had the sort of like crystal clear reproducer, a lot of the subsequent 30 or 40 minutes is us sort of like on the spot, having just found this specific problem, trying to let's call it a blameful postmortem on a particular construct, right? Like, is the problem that we used a channel of size 1? Is the problem that we used like select with a mutable future? I think we were pretty uncomfortable with select, sort of like generally, because we'd had problems with select and cancellation, right? On the podcast we haven't had yet about async cancellation, but select is a big source of that too. So I think this happened like when Dave's RFD got picked up by Hacker News and other websites, a lot of people landed on select. So I think Dave, you and I, pretty soon after that meeting, we were like, I don't think this isn't specific to select. Like we can rewrite this
Yeah.
reproducer without using select at all, using any of these other like concurrency within a future without parallelism constructs, like futures unordered or even futures ordered, like all of those, anything that lets you pull multiple futures. Well, not anything, but like there's sort of like a specific set of circumstances that is not specific to select that can induce this behavior.
In fact, that was most of the like prior art for discussion of this specific category of issue in async Rust is a blog post by Without Boats, which deals specifically with futures unordered and how to write this type of bug with futures unordered.
Right. You've got other ways of getting into this exact issue. And no matter how you get into it, it's really not easy to debug. I mean, I've always said that like deadlock in a traditional threaded system, deadlock is kind of a straightforward problem to debug because as our colleague Cliff Biffle is fond of saying, the program counter is actually a very powerful piece of state. And when you have deadlock between traditional deadlock, ABBA deadlocks between two threads, like the system is stopped, and it's stopped in a way that if you can understand where these two threads are, you can understand the lock ordering violation. It's actually not that hard to debug traditional deadlocks. Live locks are harder to debug because the system is moving, but it's not making progress. And where however you are constructing the live lock, you are not able to make progress because these two actors or multiple actors in the lowercase a thread sense, are not able to satisfy a condition that allows them to collectively move forward. But I feel like this is something different. I felt like this is like a different kind of pathology because there is, when you are locked up on where you've got one future depending on the kind of a future being executed on another arm like this, or a future that's going to be executed by the same task, however that is, whether it's another select arm or what have you. There's not a great way in the system to be like, hey, by the way, can I what are all of the futures that exist in the system? It's like, the system doesn't have a way of answering that question.
Well, can I pause for a second there, Brian? Because I think you said something very important about deadlocks are easy to debug, but I would just observe that we've made deadlocks easy to debug.
Yes, that's right. That's true.
We've spent a long time, we've spent a lot of time with this multi-threaded model where it's got this nice property that a thread can be at one place at one time. And as Dave and I and others have discussed, with tasks and futures, you don't have a stack. You have a tree. You have a tree of the multitudes that any task contains about all the places in code that it logically represents. Also, in MDB and debugging and the work that we've done for many years, you can walk up to any lock and say, "Who owns you?"
Yeah.
What's your state? And there's a lot of complexity introduced by async Rust, but then there's also a lot of that kind of experience and tooling and observability that's also absent.
Yeah, and a case I would make about this issue is that I don't think this is a fundamentally novel kind of bug. It's a fundamentally novel to async Rust way of writing that bug. And I think that distinction is actually pretty important. This is kind of a normal non-reentrant mutex deadlock. It's just that the way in which you are contending that mutex twice on the same thread in two different places is very unobvious to the programmer. The issue here, the unique thing about what is Futurelock is that it's a combination of language constructs that conceals where you have accidentally written a actually pretty traditional non-reentrant mutex deadlock.
That's a very good point, Eliza.
The way that async hides it from you, that's what makes this interesting and worth discussing.
I think
that's a very good point. Yeah.
That sort of misses, I think, that there's this mental model I think that people have, and that I think at least the traditional presentation of async Rust tries to provide, which is that tasks are sort of like threads, and you can sort of write sequential code with a wait, and it's kind of a lot like threads. But this is a failure mode. At least I don't see how it's the same as anything that can happen in a threaded system. The closest thing I can think of is this is sort of if the kernel scheduler woke up a thread and then like didn't put it on a run queue. Woke up a runnable, like took a runnable thread that was just woken up and didn't put it on a run queue. And that's not really a thing that happens. I mean, only because that software is so mature now, but like that's a weird thing to be able to introduce in the userland sort of analog.
I'm gonna push back on that a little bit. And the reason I'm gonna push back on that is because I think, well, if you write only straight line async await code and you spawn a bunch of futures that just do sort of straight line sequential await, and you treat tasks as being the same as threads, you will never have this bug. This bug requires some primitive that combines multiple futures together in the same task and allows them to be awaited concurrently, such as a select or a futures unordered or something like that. So if you really treat tasks as being exactly the same as threads, you actually can't have this problem. It's once you get into, I'm trying to select over this like large set of multiple concurrent notifications from different sources, that you have this problem. And that starts to look like, what's the threaded equivalent of that? Is it like, is it signals? Because signals are pretty messed up, right? Like you're outside of the land of normal straight line threaded code.
So I actually do have an analog for you in kind of the threaded world. And I think because part of the challenge here is that the parallelism has now become load bearing, that the parallelism that if you do, because as you point out, like if you actually have the true parallelism in addition to the concurrency, you don't hit this. And it actually Adam, it reminds me of my favorite whipping boy, the end-to-end scheduling model. The end-to-end scheduling model was like, man, come on, it's been like 30 years, dude. Like you coming after me again? It's like, yes, just to be. I think the point.
Fair to call it green threads in like the modern parlance, just so people aren't confused. Yeah,
fair to call it green threads, and but there was this, I think it was Smulders and Co. that had originally coined the term end-to-end scheduling model, but first implemented in Solaris back in the day, imitating other systems, and bad idea basically, and had a lot of problems. Problems that it had was that if you had because you could have a program that appeared to be correct, but the parallelism that you would get from kernel schedule entities, LWPs, lightweight processes, it's only a lightweight process that could actually execute on the CPU or in the kernel. And if all of your threads became blocked in the kernel on an LWP, runnable thread at userland, a runnable thread that was not kernel schedulable, and all of your existing LWPs are actually blocked in the kernel. So the process should be runnable. The threads should be runnable. You think you're runnable from a program perspective, you're runnable. But if those things are blocked in the kernel with the dependency on the thing that should be runnable but can't run, you have this problem. So this was it'd be interesting to get into the history of this. This was kind of discovered, the people who really know the history of this. I mean, sadly, Roger, who's passed away, but this must have been discovered, Adam, sometime in this is obviously Solaris 2.0 is kind of in the late. It started in the late 80s, and it ships in kind of the early 90s, 92, 93. And it's a disaster. And it's sometime in like Solaris 2.3 timeframe where I think this is discovered. And it's bad because you have a correct program that can't actually work if they're not actually creating an LWP for every thread. And so they came up with a complete kludge for this. And Eliza, signals are involved. They came up with a signal called sig waiting, and it would drop. The kernel would realize the kernel. This is just terrible. I just don't shoot the messenger on this one. The kernel would be like, "Oh, you've got all of your threads are blocked in the kernel right now. I'm going to deliver you this signal called sig waiting." And which also even the name is like, who's waiting for what? I mean, we're waiting for a proper implementation of threads? Is that what we're waiting for?
That's like a Department of Truth on that one.
Total Department of Truth. And then so you would get dropped this sig waiting, and then the default operation for libc would be to create an LWP, and then it would potentially be able to run this thing that was runnable. And I mean, unsurprisingly, this made and actually part of the work I did again as an undergraduate. This is a long time ago now. This is actually quite literally 30 years ago. But we had a really hard time getting like reproducible performance on this thing, and it took a little while to figure out. It's like, oh, that's because like every once in a while your LWPs would like happen to get blocked in the kernel, and you would get a sig weighting dropped on you, and then be able to use parallelism that you actually always had in your program. You're like, oh wow, I've gone faster now because I've got this sig weighting. It was bad. But it was one of the, and of course the signal is still present. I think it's now basically sig user 3 effectively. And hopefully not mimicked by other systems. But it is similar to what you're describing, and I think that like I understand kind of the thrust of what you're saying, but I also feel that like from a programmer's perspective, it's like it feels like a correct program that the runtime is kind of doing dirty. Because it's the abstraction that's been provided is not behaving by the principle of least surprise, for sure.
That's right. And in a signal handler, like you're in a weird spot. It's not like you would go in your signal handler and start, I don't know, executing arbitrary complex code and grabbing locks and whatever. So I think the analogy sort of makes sense in that you've got a thread that's effectively in two places at once, but it breaks down a little bit in that people are very constrained about what they should be doing and what they typically do.
In terms of like programmer feeling, right? The point at which, like on the debugging call, when I described this construct that we'd have to have, and Dave was like, I'm looking at that felt like a miracle to me, because there are literally hundreds of places in Nexus that want to claim database connections, right? So like if we boil this down to just its reproducer, it's like you have a channel and a select with a very particular construct where one arm wants to send on that channel and the other arm tries to send inside the body of the channel. But in the actual code we have, those things were far separated and spread across like at least 3 or 4 different functions, and it could have easily been significantly more than that, right? Like the channel is hidden deep inside of Corb. The fact that we're trying to claim database connections is hidden inside these other methods. Like the select is like, it's not at all obvious that it's sending on a channel at all ever, let alone that it's got 2 different places where it's sending on the same channel, right? Like it's a very non-local reasoning kind of problem to look at.
Yeah, and it's also worth mentioning, I think that is a good thing. Like that's abstraction as far as those other layers are concerned, right?
Yes.
Corb is like, I've just got a method where you claim a database connection. It's async. I happen to do it with a channel inside, but like that's not really your business. And then above that we have the data store, which is the thing that it's our interface for making all kinds of queries to the database, and it's taking care of the connection management for you. So you make some query, you get a connection for it, makes the query, gives the connection back, fine. Again, there's another abstraction there. And then we have a couple layers above that this code is using to like go collect a bunch of data that would be useful, some of which came from the database. So that's part of what, we spent a lot of time debating about what we did here that was wrong. Right. Like which of these patterns was wrong? Is it having a borrowed future in select? Is it having an await in a branch of select? Is it using a channel with capacity 1? Is it using channels at all? Is it writing software? Like it was not that clear.
It's writing software.
Like I think we kind of went around and we went in circles.
Yeah, right.
And it, something Bryan, you said a long time ago, which is like when engineers are struggling to come to consensus and like really disagreeing, the answer is not actually clear. Like we just don't have enough information to make that determination. And I think it's sort of similar here that none of these things is the bad thing. And that's part of what's sort of a gut punching moment for us, where we're like, what do we do? How do we not have this problem again? Yeah, and I think the answer is like all of these things together, and we just have to be careful when we see any of them, is kind of what it boiled down to.
Yeah, what really hurts about this is that no individual piece of this is wrong. No one is at fault. Yeah, right. And this is where a recent Brian Cantrell Blue Sky post came from our discussion of this.
Right.
Where I said, all postmortems are blameless, but this one is especially, or more blameless than others, and Bryan immediately had to post that on Blue Sky.
Which everyone assumed, by the way, was a reference to the AWS outage, which I thought was kind of funny. I'm like, no, that's not the AWS outage at all. Yeah.
And like, we spent a long time, myself included, in our discussions of this, like really trying to find a way for Tokyo to have been at fault here, right? Both in our investigation of the bug, but also in our sort of like post-mortem discussion. We spent a lot of time thinking, like, could the library have provided an abstraction that is less leaky? Could it have documented behavior more clearly? Could it have done something to stop you from doing this? And the answer is, well, not easily. It potentially could have, not allowed you to use a mutable borrowed future in a select arm at all, but there's actually a great deal of legitimate code that is safely doing that, and that wants to do that in order to express something that, like, you have to actually do that. You have to, await some future while you also wait for some other thing, and when that thing happens, you go and do something, and then you go back to continuing to drive that other future forwards. And it's like, that's actually a thing that's very useful to be able to express in Select. And Tokyo could go out of its way to prevent you from doing that, but also that's really a consequence of the Rust standard library permitting a mutably borrowed future to be pulled. And so it's kind of like all of these pieces individually are correct. The library has done very little wrong in the way that it communicates the stuff to the user. We found like maybe a small area where the documentation could be made clearer that I think Sean did go and fix, but overall, like, no one has really done anything wrong here, and that's what makes it so sad, is that you end up in this like really bad situation through every individual piece working correctly.
I don't know if this is the right time to pile on, but I would also say that the opposite of what you're describing, Eliza, is what I like, and I think what we like about Rust. Right?
Yeah, exactly.
That there is so much about the structure and specificity and strictures of Rust that keep you from needing to like construct these constraints with your mind, like you do with C++ and memory management. Like there's so much you have to it is upon the ingenuity of the programmer to document these things, to write about these things. You don't have sort of local reasoning, and instead you have to uphold these constraints without particular support. And I think this is where I, perhaps wrongly, always feel betrayed by these async Rust idiosyncrasies, where I just feel like the thing that I liked about Rust, at the bottom, the rug gets pulled out from under me.
We had higher expectations for your Rust.
I did. I'm not mad. I'm just disappointed.
I'm not mad. Just disappointed. Like, but C, yeah, I know. C's a mess. We know C's a mess. Well, not you mentioned C++. We especially we were kind of comparing it to the RFDs 397 and 400 and the kind of the async cancellation issue. Ring the chime for future podcast episode, I guess, Adam. I'm not sure what that sounds like.
Okay.
Sorry to put work on Future. I mean, you had a very kind of good point about like, yeah, but you know what? Like, let me tell you about all the problems we don't have in this system. It's like, yes, we are. I gave a talk a couple years ago on zebras all the way down about the kind of, there's the adage that we tell or that medical residents are told that if you hear hoofbeats, think horses, not zebras. But if you actually, in software, if you're building on reliable systems, like actually what's left are the zebras. And this is kind of a zebra that's left.
Yeah, I don't remember exactly how I phrased it when we were talking, but it was something about like what's left. So Rust has taken so many of the types of runtime problems that we used to have in past lives in Node.js and C and stuff like that were crashes or surprising dynamic behavior, and made those compile time failures, and that's great. And that means that what we have left are these doozies. And I feel like we've had like 3 of them now that have been really rough.
They have, okay, but I feel this one has been less rough. Do you feel that way or no? Am I the only one who feels that? I guess it's
It's,
a
you
little
know,
easy.
the part that
I'm sitting here in the stands, so I guess it's a little easy. Why don't they send the runner? Why don't they send the runner? I just don't understand.
I mean, I look back and I'm like, look, this took us like 2 days. It felt like so much longer than that. And there was so much of those days where I was thinking, oh my God, how are we going to figure this out? I have no idea. Like, this is
Yeah.
completely contradictory. I have no possible explanation for any of this and no way to gather more information about any of this. We're doomed. It's all over. And then we figured it out. And so, like, the cancellation one it's definitely a much more prevalent problem. This is like our discovery of the impact of cancellation in our code base. That was like a much bigger version of a sort of similar thing. And the other one I was thinking of was the one over the summer that we talked about earlier, the Tokyo delay slot thing.
Yeah.
And like that was at least like a very narrow, discrete problem that like we fixed and like it's done.
And we were on the LIFO slot bug for over a week. This one was a bit shorter than that.
It was.
Oh, well, only because we reused the tooling we built during that week.
That's a good point.
That is a very good point. Yes. Yeah, and I actually did not realize that you all had done this from one instance of the bug. Honestly, I thought we had seen this again. I did not realize that we'd only seen this once, which is just really impressive, I gotta tell you. And Sean is saying in the chat, but it's also really bears the emphasis. We got really lucky with this because it happened in dog food, in our dog food rack, which Sean, you were an early advocate of getting our software up and running it for ourselves as quickly as we could, and that's just been, God, so huge, so many times over. That we were able to have this in front of us, and then able to actually debug it, and honestly had the wherewithal and discipline to kind of debug it on the first shot. So I think it could have been much worse. I guess one question is, do we think we have seen this in the past and not diagnosed it correctly?
So I don't think so. That's a good question because I don't remember a hang like that. But there's another element of this story which is interesting to me, which is that we mentioned at the beginning we're on the run up to our first release candidate for shipping live update. And one of the things we were doing, sort of jamming in at the end, is I asked Sean like the week before, like, hey, can you add to our existing support bundle facility the ability to collect a bunch of information about the update system? Because that way,
sure, that's low risk.
It seems low risk. It seems so low risk. Like if I looked at that PR, I would have been so confident that was low
absolutely.
risk.
This is great. This is going to help us debug systems in the future. This is great.
Yeah. And then like that Sunday, like 3 days after it integrated was when we hit it. So it's not a coincidence that we hit it in tests or
yeah.
And another reason I think I think there was a use of the database before, but that code path that was added ended up using the database much more heavily for many, many more queries than it was before. So it made it much more likely that this would happen. And that part feels pretty relevant.
Yeah.
I have to say, I've definitely hit this bug, and I did not realize that what was going on. Yeah. I've definitely hit this bug a couple of years ago, and I was just scratching my head, and then I realized it was fixed, and well, it turned out it didn't tickle this bug anymore.
Well, it's the kind of bug that you could hit and like, oh, I hit it. I didn't understand what was going on. I restarted it and everything worked. So like, I don't know. Yeah, it's hit again.
I definitely have seen similar pathologies in a past life. In my previous job at Buoyant, we had written at least one very similar bug, and I did come away from it with some skepticism of the use of selects in loops with mutably borrowed futures. But I also came away from it thinking, like, that's still a useful tool that is worth having, which I still believe, and didn't come away from it with a name or nearly as well-defined a sort of checklist of this is precisely the pieces that have to come together to cause the bug, which is actually what I think is so interesting about both this bug and the investigation and the writing that we've done, or that Dave has done in RFP 609, is that we have a very specific checklist of you have to have all of these features in order to have the bug. If you have any of these features but you're missing one of them, then the code is actually safe. And that is the one good thing I can say about this. It takes a bunch of stuff at the same time, and that's actually pretty well understood. Now, you can certainly still shoot yourself in the foot if those various like those factors on the fire triangle, right, where you have to have like fuel and
yeah, right, exactly.
whatever the third thing is.
Oxygen. Yeah, you get oxygen, fuel, and ignition. Yeah.
Yeah. So it is certainly still a foot gun in that like some of the vertices of the fire triangle can be hidden very deeply from the code that you're looking at. But we do at least understand it actually requires all of these factors at the same time. And if it lacks any one of them, it's safe. That's
I love this, Eliza, but it's safe ... for now, because like one of those, the spark of the oxygen.
Hey, fire safety begins with you.
That's right. But the spark of the oxygen can be added non-locally in ways that it's not clear that you have now made this toxic brew.
But knowing that gives you an opportunity to program more defensively, which I've seen Sean do. Like Sean has done some refactoring of code in Corb, which was not victim to this bug, to make it harder for subsequent changes to that code to introduce this type of bug inadvertently. It sucks that you have to do this, but
there's a little bit of an irony here too. We should have a talking point about the cancellation issue that we have previously encountered, but like one of the pieces of advice coming out of the cancellation issue was, well, you can mutably borrow a future. You can just not drop it to keep it alive for longer to avoid cancellation issues if you need to. Which I'm not saying that that's contradictory advice with the thing that we've experienced with Futurelock, but I think that it's just there's careful threading of the needle to be done here, where like a very easy way to avoid Futurelock is to have things all be running on like you don't borrow futures at all. You drop them immediately, or you spawn everything on distinct tasks. And I think it's an interesting aspect of this where it's like if you take a step in any particular direction, you're opening yourself up to new pathologies that you need to guard against in a different way. Like there is no silver bullet here. It's possible to program things correctly, but you have to be defensive in each angle against cancellation safety versus Futurelock safety versus make sure that you spawn a bunch of tasks, coordinating between them correctly, and you don't leak them or anything like that.
I think right. So using mutable futures is one of the things you do to avoid cancellations. But in this case, having a cancellation was actually one of the ways that you would avoid the Futurelock bug. A different way of avoiding the Futurelock bug is to spawn a task. So there's kind of both of those sides of things. And as Sean said, you can take a step in any direction and it'll be fine. But there's kind of an easy place to end up where, actually, you have this bug.
Okay, Rain, at this point, Sean and I were talking with someone on social media, and I just want to read something that was written, which is, they say, I suppose my gripe is with the frame that this is somehow a Rust or Rust async problem, when it just seems like a knuckle-headed coder's problem. I've done dumb things exactly like this, and never thought to blame the language or the async runtime. And I think that
it's the wicked child. The wicked child is here.
It's funny, Bryan. That's exactly what I was thinking when I saw this. Like the 4 children asking their questions. Clearly, the wicked child, and I just felt like this. I get it. I get why it's easy to blame the folks who have experienced it. But exactly, Rain and Sean, as you're saying, like this is not obvious. This is also a correct pattern for many types of behavior, and there's nothing in terms of documentation, like almost literally nothing, describing cancellation at all or its impacts, and then very little, very very little in terms of tooling that might help one in this situation.
I think, I mean, for what it's worth, as someone who prides themselves on being a tool maker, I think whenever, like, it is never the human's fault. Like, I have very much the customer's always right kind of thing, and if the tool is wrong, if something goes wrong, then the tool's at fault. Like, I think it is genuinely unhealthy to have a different attitude here. Just my opinion, but that's how I have that kind of attitude.
Well, yeah, and I think that in terms of it, Adam, you're absolutely right about the documentation, which is why I felt like Dave, you writing RFD 397 on async cancellation was so important, and then Rain, you on RFD 400, and then Rain, you're against Protive Talk at RustConf. And so I did Dave, it was really, maybe you want to like talk a little bit about the RFD, because this RFD is really, really good. 609, very, very well written, very thorough. It's so well written that a wicked child on the internet could say that it's all easy, because it's like, actually, this seems easy because Dave has explained this in a way that a really terrific explanation of this problem. And so Dave, do you want to talk a little bit about the RFD? And I mean, I know hopefully I wasn't pushing too hard on the need for nomenclature here, but I really did think we needed to help other programmers be aware of this. We had to name it.
Yeah, that's right. So I'd say there was a similar feeling when we had found this problem to the feeling we had after 397, which I affectionately call Cancelgate, which is where we're like, we need to tell everyone this, at least at Oxide, because everyone needs to be aware of this, because this is so subtle. The thing that they have in common is that the failure mode is really bad, huge impact in a production system. It's undebuggable once it happens. There's no way for the compiler to help you avoid this problem. You just have to avoid it somehow at programming time. So the only thing to really do is socialize the problem and try to come up with some guidelines for people to avoid the problem. And so we did that with 397, and we're trying to do that again here. And so, I mean, I tried to write it in terms of like, I was also trying to capture a lot of the discussions that we'd had about like where the problem was and what you do about it. A lot of the FAQs are kind of along those lines. So the RFD starts
the anti-patterns. The anti-patterns are really like, oh, hey, wise ass. Oh, do you have an idea? Oh, why don't you go consult the FAQs? Like your idea, but maybe in here.
Yeah, I mean, this might be just sort of me putting my thumb on the scale on some of the discussions that we've been having and kind of seeing if people would push back on it, and mostly didn't. So hopefully that's all right. But yeah, so, I mean, the RFD basically describes the problem itself. And an example of the problem, we kind of tried to come up with the minimum. John and I spent a while on this. The minimum reproducer that would be clear, and that a person would look at this code and be like, that looks fine. That's not going to deadlock. And then of course it does deadlock and tries to explain it. And then talks about like the different other ways you could hit it, and then given all those different ways, whether it's Tokyo Select or a stream or whatever it is, how you avoid it. That's kind of the structure of it. And the idea is, to be a PSA that's like, we should all be aware of this. And I didn't have a name for it. It wasn't that clear to me that we should. You made that case, and that made sense to me, and I'm really glad that we do have a name for this class of problem. But I was a little reluctant to sort of like coin a term for this. I'm like, this is just like a mistake we made. I mean, it's an easy mistake to make, and it's important to talk about and everything. But the previous title was something like one task, many futures, and a deadlock, or something like that. It was not. There was not a concise summary of the problem.
A little planes, trains, and automobiles, but I felt we could, do something a little tighter. I felt it would be, but it was really terrific. And then you also passed your minimum reproducer to some LLMs to see what they thought of it, didn't you?
Yes, that's right. I'd forgotten I did that. I gave the minimum reproducer to ChatGPT, like free ChatGPT, and it was like, it completely nailed the problem. It described it exactly.
Wait, seriously? You gave it the code, and it's like, this is going to deadlock?
Yes.
Wow, crazy.
I was pretty surprised by that.
Did it tell you like what a handsome question you had just asked it?
Well, of course it did. And it was a handsome question.
That's right. Wild, actually.
Yeah, impressive.
Then I asked it some follow-ups. I can't remember what it was. Brian, do you remember? I asked it some follow-ups, and it totally flubbed all of those.
And was that GPT-5 or GPT? I can't remember which one you were using for that, but yeah.
I'm not actually sure. I have the free thing, whatever it.
Yeah, and it's like, look, I am ultimately just like, I'm just a stochastic parrot. I just, lucky guess that thing deadlocked. I don't know. It looked like it deadlocked. I don't know. It was a great question is what I was trying to tell you. ILM. And then but I thought this is a really good RFD. And then Dave, I feel kind of, I actually don't feel doubly bad, because actually I think the discussion on Hacker News ended pretty good. I did submit it to Hacker News, and then when it was like immediately just like went nowhere because there was a lot going on. I did bring it to the attention of the second chance pool, which I do rarely, but I do maybe once a year. But I felt like this is something that I kind of made the case for, like, this is something that actually we wanted to get some real attention on this. And then it really, like, once it kind of was above the fold on Hacker News, it caught fire on its own. And there was a lot of actual discussion that was pretty good, I thought. Dave, what did you think?
There was a lot of good discussion. There was a lot of less than good discussion, but
there's also a world-class own in there, I would like to say, Dave. I mean, you really outdid yourself. Adam, how closely did you read the comments?
Not closely enough, apparently.
I mean, Dave, absolute killer. With their someone made the mistake. Dave basically, very cheerful and really a lot of great comments. But if with some of the less helpful comments, there was a comment deriding the names of the variables in the minimum reproducer. That these were
what an astute code review. Yeah,
very astute code review.
Thank you.
Quoting Dave saying it's really important to understand what's happening here, and the comment is, well, then maybe you should take a moment to pick more descriptive identifiers than future 1, future 2, future 3, do stuff and do async thing. The coding style is atrocious. To which Dave replies, is it possible these names are intentionally chosen and actually do carry meaning? Dave, I love you asking the question.
I'm embarrassed because I don't feel like this was a high moment of mine, but I was
obviously
annoyed, and I knew that the best thing for me to do in that situation was to do nothing.
No, it wasn't.
And I was like, look, I could explain this, and it's like kind of annoying to explain. I'm like, look, it's important that the futures are fungible, that they're opaque, and you don't know what's behind them, because that's the nature of the problem, is that the actual implementation of the future that causes it to Futurelock is like way far away from what you're seeing. That's why they're called Future 1, Future 2, and Future 3. They're fungible. But like, that's a lot more to explain, and like, the question wasn't really in good faith anyway, so I just asked it as a question because it was easier for me.
Well, it was really terrific. And you should know that you brought joy into my life in that moment. So I was just stewing on that, like looking at the comment, like, oh, God. And then I saw your reply. So it's just really great. And then there's someone else actually even had then this is the great thing about the internet. Someone else comes along with it, even like more like just pointing to the actual code, like, hey, pal, if you want the actual like real names, go look at the actual code referring to it. It's like, it's all open source. So I thought that was a very helpful and productive comment. But Dave, I thought your comment was very good, and I thought it was the best angel of our nature. That's what I have to say.
Thank you. It was, better than the drafts, I guess.
Yeah, exactly. That's right. Better than what you deleted, for sure. For sure. And then, but I thought the tenor of the comments was pretty good on there. I mean, Eliza, I know you were in there swinging when people were saying that, well, this is a Tokyo Select issue. You kind of pointing out like, no, go read this part of the RFT. This can happen with other things as well. It's not the
same person. It was the same person who said that Dave's coding style was atrocious.
That's always revealing.
Well, I would say there was a similar comment from someone on the Rust async committee, basically fixating on the use of select, Tokyo Select, and saying like, basically educating people about the appropriate use of select is a lost cause.
Oh, that's fun.
Yeah, exactly. Which is like, seems like both unhelpful and beside the point. But other than that, a useful comment.
But hey, I'd like to point out that this ended up being a #1 story on Hacker News. 438 points, 243 comments, and Oxide's compensation model did not come up. So I actually, whoever had the under on that one, you're a winner. That was
a victory.
That's definitely a victory. That is a bit of a first.
Yeah, what do you expect from a bunch of guys who all get paid the same amount?
Exactly. Exactly. This is really great stuff. I mean, extraordinary teamwork. And I mean, Dave, I think just your kind of summary of it as being like, this is to me, and honest, I hand on heart believe this. This to me is a tremendous validation of Rust. The fact that these are the issues that you're I mean, there are always going to be subtle issues in a system, and yes, like there are lots of ways that async can be better, but I still, and when we originally had the async cancellation issue, I'm like, you kind of compare it to memory safety issues in C and C++, where you can make all these same arguments that really require the programmer to be. It's so easy to introduce these pathologies, and I think, of course, our code is not tautologically bug-free in Rust, but it makes it a lot harder to introduce these things. And I think you've made it harder to introduce this kind of bug in the future. And I love your open questions in the RFD about like, hey, maybe we can get a Clippy lint in here, Clippy warning about this kind of construct.
I would like to make one very brief statement in defense of async Rust, which is that we have been doing this for, 5 years now? As Oxide in particular, and this code base has, I just ran a count, it has 500,000 lines of Rust in it.
Wow.
And it took us 5 years and 500,000 lines of Rust to hit this bug for the first time.
Yeah, no, I agree. I think that's actually the right disposition. I mean, in all honesty, I think it's like, and Dave, you were also like, and I don't think I quite, because you were like, boy, every day I would be looking at a core dump. This is back in the old country of a problem that could have been caught today by the compiler, and I think that's a good reminder.
Yeah, for sure.
So Rust haters should not be viewing this as fuel for their argument, because it really does not fuel their argument. This is not. I don't think, change our disposition towards Rust at all. Rust async haters, more complicated relationship. But Eliza's right.
I think one of the things in general that would really help is better observability for some of this stuff.
Yes.
And I think some of these problems are not, like, some of these problems are inherently harder to solve because futures are passive and so on. But I think there are many things we could do here, maybe Tokyo layer, maybe within MDB, which I hear stands for modular debugger, or you can add modules to it. I don't know, but it would be interesting to it would be interesting to kind of explore kind of that thing, right? Like you mentioned that deadlocks are easier, are relatively easy to debug, and I think Adam, something like that's just stuck in my head, which is that we made them easy to debug, right?
Yeah.
So what can we do here?
No, Rain, I couldn't agree more. I think my frustration, I think I count myself now as a Rust async hater because I think they let the implementation and the evangelism of it so outstrip the documentation. And I don't mean like Oxide's generated documentation about these pitfalls, but I mean kind of like the official Rust documentation outstrip the documentation and far outstrip the tooling and the need for tooling. And instead, I think we've accidentally put people in a situation where the promises of async were use it, don't sweat it. It's like threads, but better. But then once you've written 500,000 lines of code, you start finding some of the pitfalls, and it'd be nice to have those pitfalls up front. The lessons for how to avoid them and use things appropriately. The times when programmers do have to uphold abstractions with their mind, and the compiler's not going to help you, and then the tools to help you solve when you encounter these problems.
Yeah, for sure. Well, if we can get at least on Futurelock, there is actually reason to believe that Clippy might be able to help us out, which would be amazing. Again, great work all around. It was definitely exciting to get to watch, and it was really loved watching. And thank you for your reading, your reenactment of. I love this reenactment of debugging, Adam. I think that this is like you can imagine like having, centuries from now, we're going to have debugging reenactors that put on authentic 2025 garb and
do table reads of chat messages
of debugging Rust async problems. So I think that debugging Futurelock, but I think it was really terrific. And it was a lot of fun to kind of watch that moment of great realization. And John, congratulations again on that. Just that feeling of reproducing it is so overwhelming. I feel it is really one of the unique things in software engineering to be able to go do that. And to be able to do it from, again, the single occurrence of this is just remarkable. And yes, we killed them. What's that?
I definitely slept better that night than I had the 2 previous nights. No question.
That is awesome. Well, again, great work. I'm hoping we can reduce your need for Geertra in the future. Amazing work on that, but that is definitely where that tooling gap lives. So it'd be great to go address some of that. But really terrific stuff, and a great way to use the tooling that Sean and Eliza developed for our previous problem to be able to help hem this one in a little bit, because I think it ended up helping to constrain it all. So Dave, you're saying in the chat about a poor old Corb. So actually, what it reminded me of is in back in the day, the Jeff Bonwick had that son rewrote kernel memory allocator. This is the slab allocator that was then adopted by a lot of other systems, including Linux. And the memory allocator the kernel memory allocator has extraordinary debugging to debug memory encryption problems. And part of the reason that Jeff had to do that is because when he rewrote the allocator, he now owned every bug in the system, because it would die. I mean, especially in a memory unsafe system, like you die in the memory allocator. You corrupt the memory allocator state. So he ended up having to do a bunch that was really defensive to be able to quickly exonerate the memory allocator. And, over the years, you got to the point where it's like, okay, we actually know it's not the memory allocator. And Sean, just to you have one. We've got a lot more debugging in Corb, and as you say, like Corb is actually you've done some refactoring to make it more defensive. And so I think each of these issues makes Corb stronger and better, even though Corb itself is not to blame. And I think it also gives us confidence in Corb going forward. So poor Corb, but Dave, it's Corb is it's serving its purpose well and really establishing itself as infrastructure that we depend on. All right, thank you again, everybody. We are so Adam, we are out next week, correct? And we are going to be back in 2 weeks, I believe.
Right.
For what would be founder versus investor, but is actually founder versus investor. Is that right?
Yeah.
It is going to be it's going to be a scrum of founders v investors are going to be reading. So if folks not get a chance, now time to get a quick read of the this is by Elizabeth Zalman and Jerry Newman. We had Jerry on a couple weeks ago, or 8 months ago now, maybe. But and Liz and Jerry are both going to be here. It's good fun. I've got some hot takes in the book. I don't know if that made it all the way through, but we've got some.
Yeah, I got some hot takes. I'm just hoping I'll be able to get a word in, because it's going to be a lot of confidence that everyone is bringing to the show. So
it's going to be a lot of confidence. Confidence will not be in short supply. No. And it should be fun. Join us then. And we will look forward to a podcast episode on async cancellation. Clearly, we need to go do that. Rain, I'm so sorry that we have not forced you to go to RustConf instead, but we'll definitely look forward to a future episode on that.
Yeah, sounds good.
Awesome. Thanks, everyone. See you next time.